Okay. Okay, that's fine. And I'm just gonna share my desktop here. Um, While I get started, I was wondering if I can sort of go around the room and sort of, I have a few questions for all of you. So, okay, let's see. Can I get a little bit of a feel for like who's in the audience? Like, are these, engineering students or computer scientists, or like, what year? Is everybody a programmer? Like, does everyone write MATLAB or something? Like,
Yeah, so IM UT is housed at the Odin Institute here
okay,
at UT, which is the home for computational math and engineering.
okay,
So I imagine there are a lot of students, PhD students in computational math and engineering here, most of which
okay.
probably are very familiar with MATLAB and Python, and maybe also know some C, C++, and Fortran as well. I've also seen some professors affiliated with our program, and I'm sure there are a good amount of CS, EC, um, and, uh, and affiliated students as well. Um, we,
Fantastic.
yeah, yeah.
That's very helpful. Thank you. Um, what I'm gonna do is suggest. Can I see can I see the comments here as people write them? What I'm going to do is if everyone in the Zoom comments, right, can put which programming language you use, right? Like, and it may be more than one. Like, are you a Python user, R user, MATLAB user? Maybe you already are a Julia user. I always like to start my talks by asking people what programming language are you most familiar with, and which ones do you use, and say a little bit about what you do, right? Like, I use MATLAB for image processing, or use Julia for operations research or computational fluid dynamics. Like, just put that in, and then as I get started, I'm going to sort of jump in and see, oh wow, this is fast. I can, okay, I can just open these up right here. Mostly Pythons, MATLABs, not surprising. We have a few Julias in here, but mostly Pythons, and there's second Julia. And what do you guys typically use them for, right? So there's, okay, you got computational oceanography here. Forced to learn Julia by advisor. I would love to know what the advisor is forcing you to do. But connect me with the advisor. I would like to give them a big thumbs up. Okay. So yeah, it looks like we have people from all over the place, right? You got computational chemistry, you got computational math, geoscience. Like, computation is in everything, right? And even like, I'm going to come back to this in a little bit, but since this is a computational audience, this is my sort of home playing field in some sense. So I can do more interesting things. And even before I start my talk, let me talk. A lot of my talk is just going to be sort of free form, and like, showing you, like, this is not going to be a talk that will teach you Julia, although I will show you a few tricks as well. But what I'll mostly focus on is navigating the Julia ecosystem. What is it that we're doing? And I'm going to sort of load up a bunch of different sites and sort of pointers, if you will. And one of my favorite links when I talk to computational audience is this class that Professor Alan Edelman teaches at MIT, which is Introduction to Computational Thinking. And this is it's a very beautifully created class. Some of the lectures were done by Grant Sanderson, or people who you might, or someone who you might recognize as 3 Blue 1 Brown. And it's really a basic introductory class that covers like many different ideas, but it reimagines computational thinking using the Julia language. And I'll come back to this a little bit later, as in the why Julia, right? Why Julia? Why should you care about Julia if you're a computational scientist? Um, but broadly speaking, I think of this as two ends of a spectrum. When I started my work on Julia along with my co-founders, and by the way, we just finished. Oh, I have to show you this. So this was it's been 10 years of Julia since we announced it. So we announced Julia 10 years ago. This is, if you go to julialang.org and then go to the blog there, you can see this article that we just posted, why we use Julia 10 years later. And it's actually, 100 odd people who have shared their perspective on what got them interested in Julia in the first place. And I would sort of suggest reading this. It's a really fun read, because we announced it on Valentine's Day 2012, and now it's yesterday was day before was exactly 10 years ago, 10 years later. So this is why we started Julia, right? We started Julia to solve the two language problem, right? The fundamental thing, you heard the marketing, right? As easy as Python, as fast as C. And that is exactly why we started Julia, because when we started, it was not clear that you could have a single programming language that could do performance and productivity. My own PhD is in computational sciences, and I spent a large part of my PhD writing MATLAB and then CMPI. So MATLAB for prototyping and then CMPI for scaling it up and making it accessible from MATLAB. Years of my life spent in writing things like MEX codes, and then I eventually moved to Python for one of my own computational projects. Specifically, CircuitScape is the project that I am an author of. And CircuitScape is, it doesn't matter what it does, right? It's basically a computational ecology tool, right? And it started its life in 2001 as a Java program, moved to MATLAB, was incredibly slow, moved to Python, which was what I did, moved it from, I did the MATLAB implementation, then I did the Python implementation, and then one of my colleagues, Ranjan, did the Julia implementation. Today, finally, this program has been implemented in the fourth time, and it's a million times faster than the first versions from a few years ago. And it's just amazing to see, right, that when we moved it to Julia, the kinds of problems that we could solve, right, massive amounts of satellite data processed to sort of identify what landscapes to buy in order to sort of, for conservation, right? And it's sort of a real connection from like, hey, if I solve this two language problem, if I can write in Julia so that I have the ease of Python or MATLAB or R, but with the speed of C, if I have that basic broad promise, then what can I get, right? And CircuitScape, for me personally, is this example of, we could use Julia to build this thing in which is basically a couple of thousand lines of code, but the impact is, is tremendous, right? So there have been, close to 1,000 citations of this work, and it's pretty much used for making every conservation decision today, or as an input. It's not, the only thing, but it's an input. And especially with climate change, right? Like, it's the amount of computational demands on domain scientists have increased tremendously. And, I strongly believe that the way we will make progress in our field of computational science is not by writing lots and lots of slow code in easy to use languages and then having a bunch of professional C or Fortran programmers who will convert those things and make them run at scale, but that we need to democratize it so that each and every single one of you here can use thousands of CPUs or hundreds of GPUs, or even just write use SIMD instructions on your CPU, which you often cannot use in most of the languages that you work with. Like, we want to arm every computational scientist so that they can do things on their own instead of having to sort of hand their code over to someone else for scaling. And just imagine, right, if every computational scientist, because you gave them a new tool, could just become 100x more productive in terms of what they can do, just imagine the impact on the world, right? Just imagine, like, if I'm building a climate model, if I'm developing a new drug or a vaccine, if I'm doing, just about anything else that matters to the world today, if I'm planning a new space mission, right? Like, arming computational scientists to be 100x better, faster, cheaper is a huge impact on the world. And that's how I myself, as a computational scientist, define, my purpose in life, my mission. It's what we do at Julia Computing, in the company that I'm a CEO of. That's what we do in the Julia community. And forgive me, I have a few slides that are a bit marketing oriented because, I sort of try to use the same deck for all my talks. But I promise you, this is not going to be a marketing talk. It's actually a technical talk, but I'll use a few marketing slides. So, with that, let me do a very quick round of what is Julia, right? You heard the promise. This was our starting point, right? So all the two language problem. Technical computing is just stuck in a rut today with 30-year-old technologies. I mean, everything that you use today, like all those, let me go back to the chat here, right? All these things, were written in a century that started with 19 instead of 20, right? Like in the 1990s or the 1980s, some of these things. Very, very few things are actually, except for Julia, were invented in this decade, or even in the last decade. And that's what really this is about. And now broadly, I feel like there's three major opportunities here, right? There's Julia, the language, which is composability, which I think, gives you 100x improvement over existing tools and languages and so on and so forth. Oops, this is moving on itself, sorry. All right, let's see. The second thing is that, there's the cloud, but, cloud gets you scalability, and not everyone has a cloud, but maybe some of your supercomputers at your disposal. Everyone has a large, big machine with hundreds of cores or a few GPUs at their disposal, right? So the automatic parallelization is another source of 100x speed up. And then combining machine learning with science is another 100x, right? And when I say machine learning, I'm not referring to what, detecting images of cats, or all the sort of machine learning stuff you hear from Silicon Valley, but the broad idea of differentiable programming, where if I can take an arbitrary program, differentiate through it, combine it with neural networks, can I do interesting things that I could not do before? And I will share a few examples here today. I know that Chris Rackauckas, who might join us later here today, or he might even be scheduled for another talk, he'll talk about sort of the broad idea of scientific machine learning. But in my mind, each of these gives you 100x, right? You can get 100x better by just using Julia. You can get 100x better by using cloud or supercomputing or GPUs, and you can get 100x better by using machine learning, because you can train models to approximate complex calculations with much simpler models and get a speed up. These are composable speed ups, right? So, it's 100 times 100 times 100. So if you are using something like one of these existing languages, there's the potential of being a million times better, right? 100 times 100 times 100. And that's what is available on the table for very little cost to any of you. And that's the thing I would like, I'm intentionally sort of using very large numbers here to challenge you, so that, if there's one thing that you walk away from this is that, oh, that Julia guy, he said that I'm leaving a million X performance on the table. Let me just go back and look at some of the things he said. I'm sure that you will end up in a better place. Okay. By the way, feel free to ask me questions. I'll keep looking at the chat every once in a while. I always like real-time questions rather than, backloaded. Julia is huge in the universities, right? Today, over 1,500 universities are using and teaching Julia. I'm sure that even at University of Texas, there's tons of users, tons of courses. I think someone already said that their advisor forced them to learn Julia. So I'm convinced that this logo needs to be added to this slide. There's just no way to put all the logos here. But one of the things that really excites me about Julia is the packages, right? There are 6,000 Julia packages today. And people keep asking me like, oh, but I come from Python, I come from R, why should I learn Julia? And the first thing I tell them is, you don't need to learn Julia. I mean, no one's forcing you to learn Julia. If you're happy with what you're doing today, you don't need to learn Julia. But if you tell me you're never going to use large data sets, if you tell me you're never going to want to use a GPU, if you tell me you're never going to use multi-course or multi-threading, if you tell me you're never going to want to sort of, get better performance, then yes, you don't need Julia. But my guarantee is everyone will, and they'll need to come to Julia at some point. The second question that people ask is, okay, but does it have the packages? And Julia has over 6,000 open source packages today. And what's interesting is that on GitHub, they're all sort of part of Julia organizations, and there are over 100 GitHub organizations, and they're kind of all variations on the Julia logo, themes, and colors. So, there are organizations for everything, right? Like for ecology or for climate science or biology or category theory or debugging or databases and data science and controls and machine learning and deep learning and everything, right? Scientific machine learning right here. And it's these communities that have sub-communities within the larger Julia community that sort of have a focus on solving particular classes of problems, is what makes Julia phenomenal. And many of these do not have similar things in other languages, right? And that's why if I look at the jump packages in Julia, right, like there is no similar jump or jump quality thing in many other systems. If I look at SciML that that Chris Rackauckas is working on, there's no equivalent anywhere else. And I think this is really what's drawing a lot of people to Julia today. We do an annual JuliaCon every year, and for the last 2 years it has been online. This year, it is also still going to be online because of Omicron. And we are, last year we had 43,000 visitors, 30,000 in 2020. This one's going to be online. All the videos go on YouTube. So if you go to the, excuse me, if you go to the YouTube channel called Julia Language, the Julia Language channel on YouTube, every single video from every single JuliaCon is available there. So, that's, and the reason I'm doing a Google search of these links is so that you can see me find these things and so that you can find them on your own as well. The thing that I like most is that if I search Julia today, I no longer get Julia Roberts as the first hit. I get the Julia Language. I'm curious to see if all of you get that as well or not. I'm sure Google kind of tweaks the results for all of us, and it's a little bit of an echo chamber, but you do let me know in the chat who gets Julia Roberts instead of Julia Language. But I'm sure it's going to be top 3, even if it's not the first one. All right. So the community is growing rapidly. I think that there are broadly about 1 million Julia users in the world. We're at over 38 million downloads, millions of YouTube views. Like, I demonstrate this data just because, engineers, all of us love data, and, people want to see, like, is this a real community, and is this growing, and is this, fun to participate in. I would highly recommend joining the Julia Slack if you're a new user. The details are all on the julialang.org website. The Slack is where you can connect with a bunch of people. It's real time. It's really fun. It's fast. But for any engaged, detailed conversations, they usually happen on the discourse forum, discourse.julialang.org, and that is right here, or on the GitHub issues of the various language packages and products. So this is a discourse has over 10,000 users in it. Okay, I'm just not going to go full screen because I'm changing things quite a lot. So what do we do as what we do at Julia Computing is that we participate in the broad open source Julia community, but then we build this cloud platform called Julia Hub, which is the easiest way to run Julia on the cloud, and it's largely focused on enterprises. And on Julia Hub, we provide a number of domain-specific apps like Pumas for pharmaceutical simulation, Julia Sim for physical simulation, Cedar for circuit simulation, and so on. And I will say that some of these domain products are actually proprietary products, but all the underlying stuff in it is actually open source, like modeling toolkit, for example, or a lot of the compiler enhancements that we do. So, and then this is a whole talk by itself, right? That what is open source, what is not, what should be open source, where communities can be built and where businesses are built is a completely different topic altogether, which I will not get into today, but it's something that I have personally spent a lot of time thinking about and have learned over the last few years. But I want to sort of give a little bit of a feel for like the kinds of things people have built on top of Julia before I jump into the language. Pumas is a pharmaceutical simulation, modeling and simulation tool that has been built by our colleagues at Pumas AI, and it is being used for all of your modern, vaccine and drug approvals that pharmacometricians are doing today. And a lot of it is basically differential equations under the hood. But it turns out that you can also do similar things, when you can use Julia and scientific machine learning to speed up things over, languages like Modelica. I didn't see a Modelica actually out here, now that I think about it. Are there any Modelica, open Modelica users in the audience? So no one's sort of doing equation-oriented modeling kind of stuff. Okay. So, Julia Sim is a tool that we are building that, again, at Julia Computing that leverages Julia to build a domain-specific package called Julia Sim that accelerates computational simulations by hundreds of times by using machine learning and by using new modern compiler technology. And a lot of this actually boils down to what makes Julia fast, and I'll be spinning up the Julia REPL very quickly. And the same thing with Cedar EDA, right? So one of our fun things was that Julia was on the Williams Formula One car, one of our customers, and that's really sort of what I'm excited about what we are doing in the Julia community, and especially what we're doing at Julia Computing as a company. But I don't want to make this all about the company. So with that, I'm going to transition my talk, giving you a flavor of a little bit of everything. Okay, so this is, let's go here. All right, so this is Julia Master. If it breaks, it serves me right for using the latest master release of Julia, but I literally just pulled this today and compiled it. And as you can see, it's a 0 days old master. And what I wanted to show you was, what is it that really makes, what is it that's unique about Julia, right? And if I had to answer this, it's very hard to give a quick answer, right? Like technically what's, what makes Julia special. But my one-line answer is it really is multiple dispatch. And if you really want to understand what multiple dispatch is, you should check out Stefan Karpinski's talk at JuliaCon. If you just Google Stefan Karpinski and multiple dispatch, most likely you'll find it. But let me give you the quick version of it, right? So if I do 1 + 1, of course I get 2, right? But what's happening under the hood? So I can ask Julia, okay, what are you doing when you really do 1 + 1? So I can say at which, and then it says, oh, in this file at line number 87, I'm actually, calling this particular method. But then what happens if I do 1 + 1.0? Turns out it's calling a different method, right? And at this point, you should already be thinking, right? Wait, the definition of 1 + 1 in Julia is implemented in Julia and not in the bowels of the compiler. To me, when we started Julia, that itself was a revelation, right? Like the fact that something as fundamental as just adding 2 numbers is not somewhere deep inside the compiler, but is actually just an outcome out of the basic language definition and construct. And you can now go ahead and ask what happens when you do 1 + 1 + 1, right? And I can look at the underlying assembly code by typing at code native, and I get this. And if you are an expert assembly reader, you can try and make sense of what this means. Chances are, if you're a computational scientist, you don't particularly care what it means. But the reason I show you this is that what makes code fast, right? Usually what makes code fast is that when you compile your high level Julia or Python or whatever program down to assembly code, right? Finally, the computer has to run something. It's running assembly code. And if that thing is compact, if that output of the compilation of your program is as tight as what a C compiler would have done, then you're going to have very good performance. And Julia actually does that, right? If you did this in C, you probably would have something really tight as well. And if I go into 1 + 1.0, I actually get a different thing, right? Like, here I had this LEAQ, for example. Here I have this, and you can kind of, even if you're not an assembly expert, you can kind of see what, like, CVT is convert SI signed integer to signed double, right? So, okay, it's converting this 1 to a 1.0, and then it is doing a floating point addition and then returning. Okay, so that's great. But if you did this in Python, this would probably boil down to dozens or hundreds of assembly instructions. And that's fundamentally what's different between an interpreted language and a compiled language. Julia is a just-in-time compiled language. And because of its design decisions around multiple dispatch, we've been able to have a very compact programming language definition and a compiler where even the most basic and primitive things like adding 2 numbers are not part of the language, but they're actually part of the broader system. And that allows us to do optimizations at an amazing level, right? And so the question I often like to ask is, so people often ask me this question, right? Like, what makes Julia fast? And the answer is actually, it's the design of Julia that makes it fast, right? The fact that it's multiple dispatch and it has this just-in-time compiler that can generate compact assembly code. And think about like compounding this all the way down to, all the way to like a program like CircuitScape or Pumas or Julia Sim, right? That we build all these composable abstractions all the way down from all the way up from 1 + 1 at the bottommost layer to building amazing libraries, the 6,000 packages, to building, the SciML tooling, to building sort of all the graphics and visualization tools, and then adding all the automatic differentiation capabilities in the Julia compiler, being able to sort of differentiate entire Julia programs and compute derivatives, and then wrap it all up in an industry requirement and building sort of products that are powering today's innovations, right? Whether it's, like I said, space missions or drugs or or anything of that sort. And this is how it all stacks up, right? And you can draw a straight line as a computational scientist from your tools all the way at the bottom to impact on the world, at the topmost level. And chances are all of you are sort of somewhere in the middle of this stack, right? Like maybe you are a numerical analyst, maybe you're writing a machine learning library, maybe you're an application developer, or maybe some of you might be language developers or compiler writers, in a computer science program, right? But it's all of these that get stacked on top of each other. And the fact that in Julia, all of this composes, right? That compiler writers compose with library writers who compose with application writers, and everyone's talking the same language and the same platform. And that's what makes Julia really powerful. You don't have to go and learn a different language. You can be in the same thing. And so this is really what makes all of the Julia magic happen. That a lot of it is technical, but a lot of it is social as well. But let me come back to this multiple dispatch thing, right? So if I go back and do methods of plus, right? So this is multiple dispatch at work. So when you start Julia, there are 206 definitions of the plus method, okay? And let's go to number 1. Okay, there we go. So this one's, exactly the one that we just did 1 + 1 on, right? But what if, they're different, right? Then you get into, what if instead of 1 + 1, I'm doing 1 plus, big float of 1, right? Like, so for example, if I do 1 plus big of 1, oops. Right, and then I can go and start asking these sorts of questions, right? So I got a big float back. And the question is, what is a big float, right? So big float is arbitrary precision, right? So let's, am I going to get this right if I try this out? So let's try factorial, right? For example, let's see if I can find a factorial in my definitions. Okay, I can't at the moment, but is there a factorial built into Julia? Let's say, okay. All right, so let's do this, right? So factorial of 5 is 120, right? And factorial of 18 is that number, and factorial of 20 is that, and 200. Well, doesn't work, right? Because it overflows. So I can now go and convert 200 to a big integer by just putting big in front of it, and then I get that, right? So what is happening is that if I look at the Julia definition for factorial, let's say factorial. This is going to be an interesting exercise, but let's do it anyways. Right, so I can go and look up, how factorials are implemented. Now, it turns out that in 64-bit integers, you can only go up to 20 or 21 before it overflows, and as a result, we just build a table and store all the results right away, because there's no point computing the factorial. So we do a little trick already. But then if you want to go beyond that, then you have to do big float, and then when you do the big float, let's like this, right? So let's see which method is being called here. And so now it's calling this one, and then it's going and calling a completely different factorial method when I'm giving it a different kind of input number, right? So this is single dispatch still, but multiple dispatch, for example, is when you have multiple different arguments, right? So the plus method, for example, when you're working with, if you're adding a Hermitian matrix with a uniform scaling matrix, then it's going to dispatch to this particular method, right? So broadly speaking, multiple dispatch is a way of picking what exact code to compile for a given set of input arguments. And what makes Julia so fast is that it's able to pick the perfect, most optimal method at any given point for any given operation that you write. And that's what makes Julia fast. So when in Python, if you do A plus B, Python will look at all these methods that it has, but it will do them, it's going to interpret them. So it has to look at this table every single time and then come up with which method to use at runtime. Julia does it at compile time. It will look it up, it will find the perfect version, and then substitute that in, so that when it does it, when the code is compiled and run a million times, it just works out of the box. and it's as fast as C. In fact, if you look at, like as a computational scientist, right, like one of the things you might do is you might want to do, these kinds of things, right? Like, so here's a million Gaussian random numbers, right? This code is actually written completely natively in Julia, right? So this is the complete implementation of the randn function. And these are the ziggurat tables. And then, as you scroll down, there's a lot of tables. Oops. And then, yeah, and up there, you have all the definitions for what the random number generator needs to be. But the entire Julia random number generator is actually written in complete native Julia itself, the random, the Gaussian one. Today we have the whole random number generation is a different story itself. And I should show you some highlights actually here. So if you go to Julia 1.7, which is the latest release, we have release highlights. And we actually have a new random number generator in Julia, which is multi-threaded, and it allows reproducible random streams in multi-threaded programs. So you could write multi-threaded Julia as a user and get a reproducible stream of random numbers. Like, I think to this audience, it will be obvious why this is a huge deal. All right, so let me just see if I have. Oh, someone got a movie called Julia. Okay, that's hilarious. But I'm sure that Julia was still one of the Google search things. Someone's used I'm not sure what the Simulink comment is in reference to, but yes, Julia has. So Simulink does a causal modeling. Julia's modeling toolkit is a-causal modeling, and it's equation oriented. Tends to be really fast. And at some point, Chris Rackauckas should tell you more about all of that stuff rather than me doing it right now. Why am I hesitant using Julia is not being able to get help like on Stack Overflow? How easy is it to resolve issues collaboratively? That's a very good question. There actually, so today I saw a Twitter post by someone from the Julia community that there are 10,000 Stack Overflow questions on Julia. But the reason why you don't see a lot of noise on Stack Overflow on Julia is because we have an even better version of the Julia community and collaboration on Discourse right here. So if you go to discourse.julialang.org, most likely you'll find answers to any basic questions you have. And this is really, really collaborative and really high quality discussion forum. And I would say that don't sort of let the relatively small amount of questions on Stack Overflow fool you into thinking that Julia does not have a strong community that is collaborative. In fact, let me go here, right? So if I go to my Slack, right? So this is the Julia language Slack. And this Slack is huge. Okay, so I mean, everything is muted because otherwise you'd just be going bing, bing, bing every second. And there's 11,500 people almost on this Slack right now. And there are channels for everything you can imagine. These are just some of the channels I'm subscribed to. But this is an absolutely massive Slack. And Slack has this thing that if you're on the free Slack, the messages kind of disappear every 10,000 messages. You can't get history. And so these messages actually all disappear every week. So it's a real-time tool. It does not, it's hard to look at what people talked about 2 weeks ago because the volume is so large, but it is fantastic for a real-time discussion. And one of the things is there is a very good help desk channel, I believe here, for example, right? And so this is a question, this is a place to get very quick answers. We have a fantastic channel called Academia on this Julia Slack here. So, where a lot of people who are thinking about software in academia are discussing things, and you can get into binary building, or you can get into writing compiler plugins or machine learning or the Pluto notebook. Have people seen the Pluto notebook? I think I'm going to show that in a little bit. Everyone knows the Jupyter notebooks, right? So Jupyter notebooks, Jupyter stands for, by the way, if you did not know, Julia, Python, and R. And Julia was the second language after Python to be added to Jupyter. But recently, Fons van der Plas, one of the contributors in the Julia community, started the Pluto project. And so It's actually amazing that, if you want to search for a Julia package, you just type its name with a .jl, which is the official name of the package. And then that's also very easy because Google just usually finds it in the first shot. And so you go to pluto.jl. And so Pluto is actually very easy to install. So if you just pkg.add Pluto, you're going to be up and running. And it's a reactive notebook. So it will update the cells. Pluto understands the structure of the Julia language. And so what ends up happening is that if you change some values on cells above and recompute, it's going to update everything that depends on the things that you changed. So in Jupyter, one of the problems is if you run things out of order, you can never reproduce. Jupyter notebooks are just very tough to reproduce because they don't understand the language that they're executing. And so I always tell people, if you're doing Jupyter notebooks, make sure to clear all, restart kernel, and run everything from top to bottom. Not the case with Pluto. Pluto is kind of a little bit more like Excel. It's reactive. So when you change values, it can actually go ahead and update the cells. So that's what's going on here, right? So you see that like you're changing the value one, like n here, but it's changing the result of n squared up there. And so that's Pluto. It's a phenomenal piece of software. And I would urge you to try Pluto if you're getting into Julia. Okay. So are variable types decided at compile time? That's a very good question. Variable types are decided. So Julia is optionally typed. So you can provide type hints to the Julia compiler. And in fact, if you're doing multiple dispatch, you have to provide those type hints because that's how Julia can pick between different methods, different functions. I would say that 99.9% of Julia programs you write, the types get decided statically at compile time, but the language is fully dynamic. So you can do bad stuff if you want to. And if you make it too dynamic, then the compiler cannot decide the types of things, and then it has to fall back to a pessimistic algorithm, and it tends to be able to optimize lesser. So if you're in tight loops, right? If you're writing like deep kernels that are just run screaming fast, and then write it with predictable types. But then if you're sort of doing your exploratory stuff at the top level, like doing your graphics and plotting and all that stuff, that can be completely dynamic because that's not as performance sensitive. So for example, like here's a equals hello, right? I made it a string, and then I can just go back and just do something else, right? And now I change the type of that, right? And so I can do completely dynamic things, and Julia has eval, which means you can even sort of evaluate code that is, at runtime. You can compile code at runtime, and Julia lets you sort of do all the Lisp-like things in terms of dynamic programming. And it's usually very good at it, and people use it in very interesting ways. Meta programming in Julia is a whole different topic, and if you're interested in all of those tricks, I would go to the Julia manual, docs.julialang.org. And then I go to the manual, I can go to meta programming. And then you can sort of, this tells you everything you can do with Julia in terms of dynamic stuff. Well, a lot of things you can do with Julia dynamic stuff. There's much more to it than what's right here. Like things like generated functions are incredibly powerful. You don't need to know all these things, by the way, in order to be proficient with Julia. My guarantee is that if you download Julia right now, I should have actually said this when I started the talk, that if you started Julia right now and followed along with me, you probably would have known 90% of what you need to know to start doing Julia. And in 2 days from now, you will have a program that will be faster than whatever else you're using. Quite likely, not always. There's always tips and tricks you always have to learn. My take is that any of you would become proficient in Julia within 2 days to start using it meaningfully and productively. But just like everything else, to master it, to master the concepts, to master multiple dispatch and how to structure programs with it and how to think about code is a longer journey. And there are some very good books on that topic. And I would recommend Tom Pong's Design Patterns book if you're inclined to sort of get into all that detail. But the good thing is that it's easy to get started, and you can master concepts slowly so that you build them up over time, but you don't have to make a heavy upfront investment before you're productive with Julia. Okay, does JIT compiling make debugging hard? It won't be, yes. So Julia is largely statically compiled, like I said, but it is a dynamic language. And so there can be cases where, some things don't get figured out or resolved until absolute late at runtime, at which point it will. Oh, we have we have Chris Rackauckas here as well, and he's answering some questions. Chris, do you want to do you want to say answer some of these questions in real time, since we're almost out of time? But Chris is the author of Scientific Machine Learning Ecosystem, so maybe you can say a few words as well.
Yeah. So I could chime in here and give a few details. So JIT compilation and compile time type checking are two separate things, right? So JIT compilation is a process for how code runs, which is separate from how code is inspected, checked, and analyzed, right? And so you can actually mix the two. So for example, you can have prior type checking with JIT compilation, which is allowed through something like jet.jl. So if you look at the jet.jl repository, you'll see that it has a whole setup for doing all sorts of compile time checks that you would expect from a language like C or Fortran. And it's actually being used within the Julia compiler to be able to prove things about functions and be able to implement compiler passes and such. So it's a fairly intricate compiler inspection kind of tool, but it's also being used, for example, in VS Code to be able to throw linting warnings about possible type errors. And so, this disconnect between JIT compilation and compile and type checking, it doesn't necessarily need to be the case. I mean, by default, Julia will defer errors until runtime, but that is just one behavior that is chosen by default and not necessarily baked into the language. I guess there's another question that is good for computational folks that I saw here, which is that about MPI and OpenMP, right? So Julia does have MPI.jl if you want to use MPI directly. Though there's also two forms of parallelism built into the language. There's distributed parallelism and multi-threading. So the multi-threading is more like OpenMP, which is like a single computer. Distributed is a form for multiple computers. And you can dig through the documentation on that. I think that showcasing the distributed parallel, well, I guess just showcasing like PMAP or something can be done relatively quickly, but
So there's a question about, I did a MATLAB multiplication on a 10,000 matrix, and it takes, so what you're seeing here, the 0.7 seconds the first time, and then a little bit faster the next time, is it's not that it's cache, it's caching the code. It's the JIT compile time that's happening there. Okay, so the first time you run something in Julia, it has to compile it, and then after compiling it, it runs fast. And so what you're seeing there is the time to compile it. And you can actually see a lot of the Julia compilers actually written in Julia itself. So if I go ahead, and let's just try to do this, right? So if I'm going to go ahead and do a MATLAB, like you said, so rand of 10 to the power of 4. And then let's say x equals rand of 10 to the 4. Oh, by the way, one of the things is that Julia will not, if you do that, it's not going to fill up your screen where you're frantically hitting Control-C to kill it, because it's printing everything that you wrote, unlike some of the other systems. But then, okay, let's do that. And then I got x, right? And I got my vector here. So I can go ahead and do a times x. And I got that. And now I do it again. And I got that, right? So the first time it took that long, and look at the number of allocations, right? 500,000 allocations. It's not what it should take for a MATLAB. And that's because the Julia compiler is running right now, and the compiler is written in Julia itself. So that's what it took to compile it. But now when you actually run it, it's just about this fast. And you can actually compile everything and save it in your system image if you need to. And there's a whole, you'll find tons and tons of people talking about how to alleviate the Julia compile time and build your own system images as you go along.
Yeah, so can I ask a quick follow-up, Viral?
Yeah.
So it's JIT compiling the actual multiplication, correct?
It is, in this case, it is not actually, right? So in this case, because these are, I'm using double precision types for which there is a BLAS function under the hood. What is happening is that the only thing that is getting compiled is all the surrounding wrapper code and then eventually dispatching to XP, to DAXP. But if on the other hand, I did, if I did random integers, right? Like then there is no BLAS version for, oh, sorry, it is not a DAXP, right? It's a DGMV, my mistake there. It's a DGMV there. But if I'm doing it integers instead of double precision, then there is no BLAS version, at which point it will have to sort of compile the whole thing. Does that answer the question? Let's try that.
Yeah, that clarifies it. So what I notice is if I reseed the matrix A, you're gonna see if I make it random again, the matrix A, you'll still see 0.05 because it's pulled that BLAS routine.
Yes.
Okay. Yeah, that makes sense.
Yes.
Yep. Compilation is based off of types, not on values. So yeah.
But so now I have new A and X, and by the way, it's a bad idea to do all of this stuff that I'm doing at the command line and time things, because in global scope, the compiler is far more pessimistic than in actual programs. But I can abuse it at the moment. So now this is actually compiling the whole matrix times vector for integers, and it's going to be terribly slow because it's not as well optimized as the BLAS one. Although we have plans to move everything to a BLAS-like speed eventually as well.
Yeah, so someone actually asked about that. So why implement native linear algebra routines in Julia instead of using BLAS? There's multiple reasons for it. One of the ones that we found to be most interesting is that a lot of BLAS routines are not optimized on a lot of chips. So for example, a lot of people use, for example, AMD machines these days. And it turns out that the fastest implementation on AMD chips is always going to be is actually the Intel MKL BLAS. But Intel MKL is actually not as optimized as it should be on AMD for reasons you can speculate as to why. And so we actually have libraries such as Octavian.jl, which outperform both OpenBLAS and MKL on Intel chips or on AMD chips.
So I think the answer is a little bit more than that, though, right? Like one of the questions, why natively implement in Julia instead of BLAS? That's a very good answer. And also that you can automatically differentiate through generic Julia routines, which you can't do with BLAS ones. However, if you just do a Cholesky factorization of a 100 by 100 random matrix or whatever, it is going to call the BLAS, right? So wherever it finds the BLAS or LAPACK version under the hood, it will call it. And you usually have to opt into the native Julia version if you're going off the beaten path.
Yeah, so one interesting case to look into the automatic differentiation of SVD factorizations, right? SVD factorizations are a case where the kernel itself does not have good defined derivatives. These derivatives, they have a lot of edge cases for if you have, repeated singular values and such, but differentiating the algorithm is just fine. So if you have a generic Julia code that it works with automatic differentiation and you can differentiate through that, then you can handle a lot of the hard cases that a lot of other, machine learning libraries and stuff don't handle.
Yeah, so multiple dispatch turns out to be a very nice, so multiple dispatch is actually a generalization of object-oriented programming, right? Like to answer this question that's in the chat right there, it's, in object-oriented programming, you're essentially doing single dispatch, right? You create an object of a specific type and then you dispatch all the methods on that type. And a very good example where that does not work out is when you have interactions between different objects. So think about like a gaming library where you have different, objects that need to collide. And then let's say if you're a square and a rectangle colliding, do you implement the collide method for the square or the rectangle, right? And so now you will probably want to have something which more generic called shape and then do it at that point and then, do all that object-oriented dance. Or you can just go with Julia and you can just kind of implement the multiple dispatch saying collide of a square and a rectangle. And this is how you do it, for example.
Yeah, so if you think about like object-oriented programming, right, you normally do like, x dot f, right? In Julia, in multiple dispatch, what happens is you don't privilege the X, right? You basically say, multiple dispatch would just say, I would write this equivalently as a function that's based off the type of X And then you would write this function, right? Now, there's nothing about that's privileged about the first value. You could dispatch off the first one, you can dispatch off the second one, dispatch off the third one, you can dispatch off the first and third or any combination, right? So it's a strict generalization. And I would actually recommend if you're interested in that, I would read, so Bjorn Strausted, I never know how to say his name, the creator of C++, actually goes into how he believes that object-oriented programming for C++ was a mistake because using this alternative syntax with multiple dispatch would give you a strict generalization and without privileging one value. And he has some nice examples of where it ends up leading to like programming issues. So I would refer back to his writing on it. I think that it's like C++ multi-methods, or if you look up Bjorn Strauss up and multiple dispatch, it'll come right up on Google.
I think there's a good, very specific question from Kevin Song about methods and methods with, and it's noisy. Yes, it is quite noisy, and I think we need a nicer viewer, but that's, I think in VS Code, we can make it look nicer. Maybe it already is nicer looking. One of the problems being like one of the original creators of the language is that I never use other tools and I just still use Emacs and the command line to program things. And so my demos tend to look uglier than what Julia actually is today like, which is that most people actually use VS Code. So if you go to juliavscode.org, then it's actually much nicer looking. So this method is going to look nicer in VS Code. But I don't know that for sure.
Yeah, the one way that I like to do a lot of search, right? So this information about types is usually in the help function, right? So if you do like, question mark Cholesky, right? It would give you this information. And so what you want to do is you want a function that would search through all those different helps. This is given by the apropos function. So apropos diagonal will search through all the different help functions inside of your local REPL, and will find the ones that mention diagonal matrices, and they'll spit all them out, and then you can use that to be able to narrow down the possible functions, which might be talking about what you're trying to look for.
Thank you.
Not sure what this comment is about.
Oh, that comment's about the creator of C++ talking about unified function calls and multiple dispatch. Yeah.
Thank you. So my talk has been a little bit all over the place, but the purpose is always to sort of give a taste of what everything looks like, rather than like here's what the syntax looks like, because everyone can always figure this out. You can also include the UT Austin in the awesome. Oh, DJ for Earth. I didn't connect that. That's the same. Yeah, that's from UT Austin. That's amazing. We'll add that logo. So, any other questions that we can take? I also want to be mindful of everyone's time. We're coming up on the hour. We are in fact just going to have the Cambridge Julia users network meeting, the meetup. It's going to start up in a little bit. So that's where we're headed here on the East Coast after this talk. Ooh, CatLab. I think this might be a Chris question. Like, there is a catlab.jl, right? I mean, am I not wrong?
Yeah, well, that's what I'd be referring to. Yes. So yeah, catlab.jl is a category theory based language written in Julia. There are then applications of this category theory language, such as algebraic dynamics for defining dynamical systems in algebraic ways. So for example, you can define, say, one way to be able to define a epidemic model, right, is you say like, oh, there's an epidemic in each city, and then you replicate it among cities according to some graph of interactions between cities, right? And so, for example, in category theory language, that's where you have a model and you do a tensor product of the model against the graph of the interactions of cities. And so things like CatLab and algebraic dynamics.jl allow for using that language to be able to quickly build up very large dynamical systems models.
Yeah, the CATLAB folks are working, yeah, and the new algebraic contracts. I don't think I knew that one. Cool. I think James Fairbanks is working quite closely with some of the CATLAB people. That's the one that I know a little bit about. Okay, so any question, can you talk a little bit about maturity, stability of the Julia API? So what we, Julia follows a semantic versioning system, smver.org. What that means is that once the major version becomes 1.0 and the current Julia release is actually 1.7. So after 1.0, we are committing to API stability so that there will be no breaking API changes in documented APIs in any minor or patch version of Julia. So starting Julia 1.0, we have not broken the language at all. And we, that's almost 4 years ago now. We went 1.0 in 2018. Of course, these things are not backwards compatible, right? So when we add multi-threading in 1.3, that doesn't work on old versions, but code written in 1.0 or using documented APIs continues to work with new versions of Julia. Increasingly, and this is one of the talks that Stefan gave at the last JuliaCon, is that a lot of packages have now gone 1.0, which means that not just the Julia language is API frozen, but also a lot of the core packages are getting, API frozen. And the next year there will be, the next ring of packages, right? So think of it as concentric circles, and the core's kind of becoming more and more solid. However, we don't want to say that, no new APIs or nothing will break ever, because semantic versioning does allow you to break things when you change the major version, so version 2.0. Right. And we are very clear that if we are going to do breaking stuff, it has to be worth the user's while in order to do it. And we've been able to do major changes in a non-breaking way, right? Like we added multi-threading to the language without breaking anything. And so, at some point we'll want to clean up some things that we don't like about 1.0, and we'll do that at some point in the next 2 or 3 years. But it's a long way to go. What do you want to achieve in the next 5 years? So that's a very tough question. I mean, there's so much, and I always get it wrong anyways. But a big one that I keep repeating over and over and over again is differentiable programming. I want everyone to be able to definitively and easily differentiate Julia, and it's a very complex topic, and Chris can probably give multiple talks on this. In fact, Chris, do you want to post your the recent AD blog post?
Yeah, I'll post that blog post. In fact, shameless plug, I will be at the Odin Institute on April 26th. I'll be flying in and everything to give a talk on scientific machine learning and differentiable programming. So if you want to get the full talk, I will be there in person. We can talk at length about differentiable programming.
Or sit down with Chris and do a 1-hour session and learn everything and become proficient with Julia while he's there. Yeah, so differentiable programming is a big one. A big major improvement, a quality of life improvement, which is not a feature but is reducing compile times. And our compiler team is spending a huge amount of time, fixing LLVM, fixing all the underlying tools, fixing the debugging experience, all of that just makes Julia so much easier to use. But that's not a fancy new feature. In fact, one of the things that we've done with Julia is that we keep, we started out with a very small language definition, and we're actually making it even smaller, right? So that we have to change fewer things and pushing innovation to be outside. So you can, for example, if you look at the juliagpu.org, right? If you go to the Julia GPU compiler, the Julia GPU project is a compiler addition to Julia that is, that's completely outside of the Julia project, right? So we made a lot of improvements to the, we did a lot of refactoring of the Julia compiler internals so that the GPU compiler could live outside of Julia so that it could evolve faster than the language itself. And now Julia GPU is evolving at a much faster rate and is probably the best is the best GPU compiler out there. Sometimes it even outperforms CUDA C++. And that to me is sort of something that we got right. We're doing a lot of refactoring again for automatic differentiation so that many different AD libraries can live and exist outside of Julia. The compiler plugins, work is also heading in that direction. So we keep trying to refactor things so that people can innovate around Julia from the outside rather than having to change Julia to get their thing to work.
Yeah, so I see that the next question in the list here is any recommendation for the best way to introduce students to Julia for programming assignments? I think that the best resource is Alan's class, so Introduction to Computational Thinking, if I remember correctly.
I showed that link when we started.
Yeah, I think that's a great resource for teaching undergrads. That's made for undergrads. There's also a grad course that we have, which of course is going to be levels more difficult for higher students. That's going to be the SciML book, right, which goes more into things like implementation of automatic differentiation, scientific machine learning, code optimization, parallelism, MPI, and all those aspects, right? So what we're all showing here is, I think, probably the best resource for undergrads. And if a grad student wants, what's the resource for them to like use Julia for research and such, I'd point to this other resource as well. And together, then it covers quite a bit.
All right, I think we are largely, I think the questions have dried up, and I think we covered a lot of ground. Well, thank you, Evan.
Yeah, I just want to say thank you. That was really great. I saw you guys at SciM CSE in 2019, and it's great to see what's happened even in the last 3 years. So very exciting.
Yeah, join the Julia, join the Slack discourse. There's just like all of us are around, and you'll like for this audience, I know that like everything that I talked about is completely relevant, and all the community channels and everything are like, you'll all be home.
All right, I guess without further ado, Shen or Shreyas, do you have something prepared for the end of the talk, or should we just give a round of applause? And,
well, is there any other final question from the audience?
all right, yeah, let's give some virtual applause hands or something of the like. A lot of thank yous in the chat is great, because this was great, and
yeah, this was
excited
awesome.
for Crit. Sorry, Shreyas, go ahead.
Oh, sorry. Yeah, this is extremely good.
Yeah. So thank you everyone for joining us on Zoom, and we will be organizing more events this semester. Please follow us on social media for updates, and if you are a UT student, you can join our chapter on HeartLink. And just thank you for listening, and thank you for the great talk, Vera and Chris. Hope everyone have a good rest of your week.
All right, bye.
Bye.
Bye. Shreyas?
Yeah.
So do you know who started the recording? I think we can stop the recording now.
Sure.